Many thanks, Martin. Many thanks, Alex. Thanks for the opportunity to talk about this very important subject this afternoon, and good afternoon to everybody else. I'm just going to make sure my slides can move forward. Oh. Let me just go back to the beginning. Sorry about this. I think Martin's already gave a brief introduction of who I am and where my kind of role within ALS. So I'm technical director of ALS. I'm based in the UK, but I've got a lot of interest in what goes on in the US. Certainly, there's a lot that Europe and the UK could learn from the US, and we've certainly been looking with a lot of interest in developing regulations, and certainly of interest in some of the site investigations, sampling, and analytical techniques which have been developed in the US. So to start off with, we're talking today about top assay. Now that is quite a widely available analytical technique, and that's perhaps one of the main advantages to it, because there's a lot of capabilities and capacities for labs to carry out analysis of top assay. It's a relatively simple method, as long as you're aware of some of the key limitations, and this is one of the main points of the presentation. I would say that there are many other analytical techniques available, which are complementary techniques. So, for instance, top assay could be used alongside combustion ion chromatography, techniques such as absorbable organic fluorine and extractable organic fluorine. And we've got colleagues across the world which have carried out analysis and done some comparisons between the data we're getting from top assay and the results we're getting from absorbable organic fluorine and extractable organic fluorine. So it's quite useful in that respect. But I wanted to talk quite a lot about why we use top assay, when we use top assay. So top assay can provide an indication of current risks and also future liabilities for sites which were impacted by AFFF, or aqueous film forming foam. So that's the main advantage, I would say. It gives you an idea of the potential concentrations of the precursors that might be present in soil and groundwaters. So, and you can have an idea of the future potential concentrations of PFAS as well. Researchers are starting to look at forensic approaches for top assay. So I would say there's quite a lot of hidden data within top assay that we don't make the most use out of. So there is quite a lot of information that we're perhaps not using to the fullest extent. But just to give you an idea of the actual method itself, if you expose some of these kind of precursor compounds or these polyfluorinated substances to hydroxyl radicals, you can convert them to the corresponding perfluoral carboxylic acids, the PFCAs. So that's the main basis of the kind of technique that we're talking about today. So for instance, if you've got C8, ECF precursors, electrochemical fluorination precursors, those will convert to P4, the corresponding carboxylic. So if you've got the C8 fluorotelomere precursors, those will convert to P4, but they'll also convert to C7 and shorter chain lengths. And you can see this kind of sequential unzipping. But this alone, that kind of fact alone might be quite useful to determine the difference between ECF and fluorotelomere sources, for instance. So that might be useful in itself. But we're gonna look at a little bit, as I mentioned, some about the limitations and some of the challenges. We're going to have at least a couple of slides on the data quality objectives. I wanted to just maybe talk a little bit about a niche use of top assay as well. We've seen it being used for foam decontamination work, which I know there's a growing interest in the US for foam decontamination as we're moving away from PFAS containing foams, or AFFF, and using fluorine-free foams. And there's this potential issue with rebound, so we can use swabs using top assay. And just a very quick glimpse maybe at the future research and development opportunities. There's been some interest in UV activation for top assay, where we might see some advantages in terms of turnaround times, for instance. And then we're hopefully going to be able to summarize all the content of the presentation just at the end. So I know there's probably many people who are very familiar with the physical chemical characteristics, why PFAS are important, but just as an opening slide, I thought it might be worth mentioning there's the kind of issues that we're seeing with PFAS and why they are so important. So we know that PFAS can be quite mobile in groundwater, especially the short chain PFASs. So that has potential to impact drinking water sources, and that's often a key exposure pathway. They can certainly biotransform in the environment, but they don't show it, they show very limited signs of biodegradation. And we know that the longer chain PFAS, the PFOS, the P4, those ones that are more studied, they're more studied because they tend to be more bioaccumulative. And they've got some interesting toxicological aspects to them because they bioaccumulate in proteins rather than in fats. So that's quite different to some of the other persistent organic pollutants we might be familiar with. And one of the main issues from humans, humans can absorb and retain PFAS for longer because they've got this kind of 4-compartment kidney, so you get this kind of renal reabsorption. So I've got a particular interest in toxicology as well. I know obviously work for ALS, we're a lab, but I've got a particular interest in risk assessments. That is my background, and I've got a particular interest in toxicology as well. I would say as a word of caution, not all PFAS are the same. We're starting to look at some of the fluorotelomere alcohols, the FTOHs. They've got different physical chemical characteristics. They tend to be more neutral, more volatile. So they would be quite different to the more studied PFOS and the P4s of the world. So just kind of an opening slide. There's many different sources of PFAS, and I just wanted to make you aware of where perhaps it is most appropriate to use top assay. I think most people are aware that the most dispersive use of PFAS is in the application of firefighting foams. So we're seeing PFAS concentrations, high levels of PFAS, wherever there's kind of fire training areas or wherever there's actually been instances of fire. So things like airport sites, military sites, oil depots, fire stations, etc. These are the common sites where we're finding issues with AFFF, and where actually top assay would be most relevant. But you could find PFAS in any large warehouses, sprinkler systems, vehicle manufacturing workshops, breweries, etc. Aircraft hangars is another example where you might see significant quantities of PFAS. There's also sources like primary manufacturing where PTFE is manufactured. Conventional wastewater treatment works, they have trouble trying to manage PFAS contamination. And we're seeing PFAS up concentrated in fertilizers. So we've got an issue with biosolids where PFAS has been spread onto land to act as an agricultural improver. And then we've got this issue with up concentration in cattle and PFAS being impacted as a result of that. But, there are other sources as well where PFAS is used as a mist suppressant for toxic fumes in chrome plating works, for instance. And we're often seeing it as in landfill leachate. But just going back to the main point, I would say top assay would be used wherever there's AFFF impact. So if you've got aqueous film forming foams, fire training areas, etc., where there's high concentrations of a number of different precursors, then that's basically where to use top assay as a technique. There are other places where you could use it, but that would be the more common approach for top assay. We've seen an evolution of laboratory analytical techniques, and you can see from here, these are the kind of standard targeted analytical methods that are widely available now. And I know in the US, they're very prescriptive in terms of the kind of methods that are used, and that's not the case in all parts of the world. But one of the things we don't see with top assay is a standardized document method, in the same way as we got kind of methods for more targeted analytical techniques. So that's just one of the limitations perhaps to be aware of, that there isn't this kind of standardized, documented approach that is used very widely for all the labs. You will see a difference between labs. You'll see a difference in the different kind of approaches that are employed for top assay. I would point you in a useful review of top assay that was undertaken by Ventia, as well as the Australian Land and Groundwater Association, ALGA. They've looked at different kind of approaches for top assay, and they've kind of come up with the kind of pros and cons of the different approaches. But other techniques have been kind of reviewed, and there's been subsequent reviews that have been carried out in other regions as well. But just as a kind of maybe a point of note, we don't see the kind of standardized approaches we see with other techniques. So there isn't this kind of standardized approach for all different techniques. I just wanted to mention one other thing, which is still related to top assay, but it just might be worth being aware of as a general comment as well. So in the UK, we kind of regulate 47 PFAS, which is very similar to the kind of 1633 approach, but we've just got a few more PFAS that we look at. And we've got different compliance tiers. And as you can see, there's different PFAS that we've kind of noted by analysing over 1,000 samples now. But it's interesting because one of the constituents of AFFF, which was considered to be a precursor and not very persistent in the environment, is this one particular compound called 6,2-F-tab. That's an interesting one because we're finding it at very high concentrations and at high frequencies. And when we've analysed it, we're seeing these kind of exceedances. So I think the very similar principles could be applied in the US because it's a constituent in firefighting foam. I think you'll find it on a lot of your sites as well. And when we use it in terms of top assay, it's likely to oxidize as PFHXA, which is one of these kind of much more common PFAS that we find. So if you're using top assay under the conditions of top assay, 6,2-F-tab would oxidize to PFHXA. I also wanted to kind of mention a particular area of interest internationally as well, which I think there's also a lot of interest in the US because I'm aware of some STIRDIP and ESTCP funded studies looking at this. So it's a particular interest in the US as well. It just is like a small mini case study. We were involved in a project where we were looking at PFAS in concrete. So concrete can be very porous, which allows PFAS to diffuse, partition and self-assemble on surfaces, especially in these kind of fire training areas where AFFF has been used over years or decades. And we're seeing PFAS leach from concrete over time, and that acts as a secondary source of contamination. So you could spend many millions or many hundreds of thousands of dollars remediating a site where you're dealing with the soils and the groundwater. But if you don't take into account concrete in your conceptual site models, you could be spending a lot of money unnecessarily. And we know in there's a growing awareness that this is a secondary source of contamination. And I think we're seeing these kind of cationic and anionic PFAS, where there's a combination of different kind of precursors that are used. And this kind of enhances this formation of bilayers and this stability. We're seeing these kind of surfaces that are formed on concrete. And then PFAS forms these what are called vesicles and lamella sheet, these kind of structures on the surfaces of concrete. So there is a particular interest in PFAS in concrete, and I can see that being more of an issue in the future as well. So we had this particular site where we had high concentrations in soils, we had high concentrations in groundwaters and surface waters near the site. But when we analysed the PFAS itself, normally there's two reasons for analysing concrete. It's to determine the depth of penetration of concrete. And on this particular site, we found that PFAS didn't impact the concrete to any significant depth. It was kind of near surface, the top 200 millimeters, the top 20 millimeters to the top 30 millimeters. So certainly very near surface kind of impacts. But it's interesting because what we also found, just as on this particular case study, we did also find PFAS at the base of the core, which didn't make any sense conceptually. But the reason for that was after doing quite a lot of research and having this kind of quite detailed discussion with our client, we found out that the bottom of the kind of concrete slab was in direct contact with groundwater. So as I said, conceptually, it didn't make sense. We've seen some high concentrations at the surface, and we also seen some high concentrations at the base, but nothing in the middle. But that kind of explained that. That was an explanation as to why there was this kind of difference that we didn't first understand. But we did find that PFAS can certainly leach from concrete. So that might be a consideration, taking into account the different leaching options that are available to us. But we certainly found that PFAS can leach from concrete using kind of different analytical tools to do that. We have a specific type of leaching test that we carry out, but I'm sure there's various different options, and I'm sure you'll find the same thing. There's been various kind of research papers that have been published on this subject, and they've all come up with similar conclusions that certainly PFAS can leach from concrete over time. I just wanted to also draw your attention to a couple of research papers that might be of particular interest. We know that AFFF impacted soils and groundwaters. It's typically formed, PFAS typically forms these kind of very complex mixtures where there's many thousands of PFAS that can't be detected by standard analytical methods. But these PFAS we know can biotransform in the environment. Some of the more regulated perfluoroalkyl acids. And this kind of paper highlights the importance of top assay and other non-target analytical techniques as well. So it talks about high-res MS and various other different analytical techniques. But also maybe just to be aware that if you're carrying out remediation and you've got benzene impacted groundwater and you're using in situ chemical oxygenation, or ISCO, as we call it in Europe, if you're using ISCO, you can actually preferentially transform some of the precursors to the persistent perfluoroalkyl acids. So this is just maybe a word of caution that has happened on some sites where there's been benzene impacted groundwater. People have treated it by using by pumping oxygen through it, and they've converted some of the precursor compounds. But if you're using top assay, you've got an idea of the potential precursors that might be present on your site. And the second paper is also a useful paper. And this can be used alongside top assay. So you would use this kind of Nickerson extraction technique, where I think this paper kind of highlights the fact that a lot of the extraction methods that are used by labs are focused on the anionic form of PFAS, but a lot of the precursors are present in the kind of cationic or the zwittionic. So zwittionic is a positively and negatively charged form. So we're seeing that you could potentially miss some of the mass of PFAS if you don't kind of adopt this method of Nickerson, and that's become increasingly more popular. So I wanted to kind of discuss some of the uses of top assay, where we would use top assay, what kind of data you get back, etc. And I think this is quite a useful visual. The technique itself, you might be fully aware of this, but top assay was developed by Erica Holtz and Dave Sedlak at Berkeley University, and it involves oxidation of the sample using persulfate, sodium hydroxide, heat, etc. So we've got this technique that kind of mimics the changes in the environment that can happen in soils and groundwaters. But it can be used for soils, it can be used for waters, it can be used for AFFF, as we've seen already. It can be used for concrete. It can be used for other matrices as well. So I've seen it used for quite a few different types of matrices as well. And what kind of information do you get from it? So top assay characterizes any PFAS that are not amenable to kind of routine analytical methods. And it does this by converting the precursors into the more measurable perfluoroalkyl acids, the PFCAs. And that's done by oxidation using the kind of hydroxyl radicals. So you get two sets of data. One set of data is the pre-oxidation data, which is a standard PFAS that you get if you're just using the more targeted analytical techniques. And then you get the same PFAS reported, but post-oxidation as well. And that's where you can see some of the useful information from top assay. So if you compare the first kind of radar plot with the second radar plot, you get quite different data. You get an indication of the changes that can happen in the environment, and this is where the top assay really comes in. So the difference between the two sets of data provides an indication of the precursors that might be present. But visually, it's quite helpful to see it like this. But that's the main advantage of top assay. It gives you that kind of indication about future liabilities of sites. There are limitations, as I mentioned at the very beginning of my presentation. There are a number of limitations that we do need to be aware of. And as I said, there's a variety of top assay methods, and I've seen some other kind of techniques that we've been talked about as well, things like direct top assay, enhanced total oxidizable precursor assay as well. So there's various different methods that are available, and there's no standardized approach at this moment in time. One of the kind of limitations of top assays, we have difficulties. There's some unmeasurable transformation products that are produced during the top assay. So, for example, if you have some of the polyfluorinated PFAS that contain an ether group, they can produce these transformation products that can't be measured by the kind of post-ox top assay. So you just have to be aware of that. That is one of the kind of limitations as well. Samples with kind of ECF precursors, they do show quite relatively high yields. So you do get some concentrations where they get kind of high yields. I would say one of the limitations as well is where you get some of the short chain fluorotelmer precursors, they show lower yields, and that's because of this kind of unzipping process that I've mentioned already. And they get converted to some even shorter chain PFASs. So those are not picked up by the conventional methods. And because of this known issue, we're starting to look at developing a method for the ultra shorts where we would be able to determine these kind of C2, C3 PFAS. So that's something we're looking at in the future. It's not something we're offering at the moment, but it's something we're certainly looking at in the future. But if we were able to determine these ultra shorts as part of top assay, I think there's been some research out there, mostly at an academic level, which do show much higher yields if you are able to determine things like trifluoroacetic acid and some of the other ultra shorts. So that's just maybe worth being aware of. We know samples with high total organic carbon, high TOC concentrations, they might not get converted under top assay because some certain organics can scavenge the hydroxyl radicals. So that is one of the limitations. On the next slide, I'm going to talk about some of the kind of ways we can get around that, some of the kind of approaches that we've developed about kind of overcoming that particular hurdle. I know with certain acid matrices, for instance, where we've got low pH, we do have difficulties reaching a pH of 13, which is one of the requirements of top assay. So there's careful management kind of required to make sure that when we're using sodium hydroxide, that it reaches that kind of appropriate level of pH. Otherwise, there's no point carrying out the top assay in the beginning. And also samples which have got high concentrations of iron. Some of the carboxylics, they can show affinity for iron oxide, for instance, and they can be taken out of solution by the precipitating iron. So that's another one of the kind of limitations of the method, one of the things to look out for as well. So that said, those are the limitations. I wanted to talk about some of the things that we can do to overcome these limitations. So in the US, our labs in the US have used a particular oxidant surrogate. So when we add an oxidant surrogate, it's a C13 labeled FOSA, and that's one of the ECF precursors. And then we subject that to top assay. And that's useful because we can discriminate it from FOSA that might be present in the sample anyway. But it's used to ensure there's sufficient oxidizing radicals, and that we know that the top assay has essentially worked. And it can be used for samples with high total organic carbon, those kind of issues that I've just mentioned. And that can be used to determine the extent to which those scavenge the hydroxyl radical. So using this it's like a quality control measure almost. It's useful for that purpose, and it is used by our labs in the US. There's many other kind of data quality objectives, and this is just a list of these kind of data quality objectives. So to ensure that it's full oxidation, we look at these precursor compounds. We looked at FOSA, but we also look at things like 6,2-FTF. So if they're detectable post-oxidation, then that might signify that if we'd seen these post-oxidation, that might signify that complete oxidation hasn't happened. So we need to be aware of these kind of data quality objectives. But there's various different data quality objectives which have been published, and I'm sure we'll probably see more in the future as well. I also wanted to point you in the direction of some latest research, which might be of particular interest to you. A lot of these papers have been published in the last couple of months, so you might be aware of them anyway, but they kind of talk about the use of multivariate statistical tools, things like a technique called uniform manifold approximation and projection, or UMAP. There's other kind of techniques available out there. This is for use with top assay data. There's other techniques out there, hierarchical clustering and various other kind of statistical modeling techniques which are available. But they're actually open source as well. So if you wanted to look at them, I've actually provided the link there. It's not something ALS has been directly involved in, but I'm just pointing to the fact that there are these kind of tools available to make more use of top assay data. And this is a direct reference from how it can be used. So please have a look at that. I think it'd be quite worthwhile having a look at that. I would say it's a preliminary line of evidence. And later on in the presentation, I'm going to talk about some of the other techniques which might be available to us, which give you a little bit more certainty of the data. So it's useful to be aware of these kind of preliminary lines of evidence. But if you wanted more certainty, if you wanted to use a technique called high-res MS for legal cases, I think that would be also a useful option as well. Now, I mentioned about foam decontamination. We've been working on a sampling and analytical technique to be able to understand the benefits of using swabs for decontamination. So we know that PFAS can absorb on the inner surfaces of suppression systems, and it can potentially rebound into fluorine-free foam during decontamination. So just highlights that AFFF can form these kind of surfaces on pipework and tanks, and there is this issue when we're swapping out or switching out the foams, and there's a growing market for this at the moment. We do need to be aware that you can get rebound from PFAS, this residual PFAS that forms on the surfaces of tanks and on the surfaces of pipework, form these kind of crystalline solids or supermolar assemblies. And if you're not aware of that when we're doing this foam decon, then this can potentially rebound into the fluorine-free foams. So we developed this approach alongside Ian Ross from CDM Smith, and also with academic partners in Sweden, SLU, which is a university in Sweden, and also the University of Surrey. And we provide kind of information about exactly how to carry out the sampling technique, but typically you'd have a template, which would be a 10 centimeter by 10 centimeter template. You would place that on the surfaces of a tank, and you would swab a specific direction, as you can see on the slide. And that would give you an indication. You could upscale that, and you get an indication of the kind of PFAS residual on the entire surface of the tank by upscaling that kind of approach. Because we're able to work quite closely with our academic partners, it kind of provided verification of the approach that we took. So I just wanted to maybe just draw your attention to this particular analytical technique that allowed us to verify this approach. So it's a technique called time of flight elastic recoil detection analysis. There isn't a wide availability of this across the world. I think there's about 5 labs that offer it, and they're all kind of academia-based labs. So this TOF ERD approach, it provides like a qualitative materials analysis, and it gives you an indication of the elemental depth profiles and gives you concentrations of the elements in the sample. So as you can see from the kind of graphic here, we've got 2 different graphics. One is the swabbed and one is the unswabbed approach. So the difference between the surface elemental composition of the PFAS impacted pipework gives you an indication of the kind of fluorine in the actual sample itself. And by swabbing the surfaces, we found out that we can remove up to 95% of the fluorine. So it was useful from that point of view. I also carried out a conventional analysis, obviously, as well, but it's kind of useful that it kind of gives us that verification that the approach that we took was an appropriate approach. But if you didn't use that, you might miss this kind of residual PFAS that is present on surfaces. Just very briefly, I've probably slightly over-talked. There's a new technique which has been developed called UV activation, which kind of optimizes some of these kind of quenching protocols and could actually produce a more robust method. And it involves UV light, which activates the KPS, and that gives you it might improve the kind of turnaround times, because at the moment we're using this heat-based approach. This is kind of a research and development level at the moment, but we've got some partners that we're working with And we might be seeing this in the future, maybe in the next 6 months to a year, potentially, when we've done some trials. But just to raise your attention to this new technique, it might give us some quite useful information in the future, and certainly has the possibility to improve turnaround times as well. Now, I did talk about another technique, although this particular presentation is in relation to top assay. There is another technique that can be used alongside top assay called high resolution mass spectrometry, or high-res MS. And that allows us to look at many more PFAS, and you get quantification of the PFAS, which is what you don't get. We know top assay is an indirect method to measure the precursors, but high-res MS will give you more data about the precursors themselves. You get that kind of quantification and identification of PFAS. We know that there's a lack of reference standards. We don't have reference standards for every single PFAS out there. So in terms of high-res MS, there's normally two options. There's a technique called time of flight, and that's provided by one of the instrument manufacturers called Agilent. And then there's another technique called Orbitrap, which is provided by Thermo. So the two different main techniques, essentially, that are part of high-res MS. And we're currently working on approaches where we're determining high-res MS, and it's how to communicate the certainty in the kind of data you get back, how you identify and quantify the PFAS. So we're doing quite a lot of work on confidence limits using this high-res MS approach, and maybe that could be a future presentation. Maybe that could be the subject of a future presentation. But I know in the US, I think as part of a CERDIT-funded study, there's also been work that's been carried out by various different academics trying to develop a high-res MS kind of library. And I believe also NIST looking at this, kind of the National Institute of Standards and Technology, trying to develop a kind of a high-res MS library. But we've been looking at this ourselves, and we're kind of pulling together some information. And like I say, it might be of interest for maybe a future webinar. So just in summary, there are many advantages to the top assay technique. And I would say that top assay can be used with other techniques. It's not a mutually exclusive technique. It can be used with total organic fluorine, combustion ion chromatography. It can be used with high-res MS. Every analytical technique's got its pros and cons. I would say there's always going to be this trade-off between sensitivity, selectivity, inclusivity. So there's always this kind of trade-off between all those kind of three different aspects. From a lab's point of view, ALS, are like many of the labs, we're involved in a lot of ongoing method development. Obviously, research is essential. Research and development is essential. We're looking at kind of advanced oxidizable precursor methods. We're starting to look at kind of UV activation as well. I know I've touched on concrete as a potential secondary source of contamination. That might be of interest to some people, where top assay has been used, and it's been quite helpful from that perspective as well. And also, we've seen that foam transition is a kind of a growing market, and unless there's proper cleaning which has been carried out, there's this potential for PFAS rebound, and then this kind of potential liabilities for some of your clients as well. So I've provided some references as well, but at that point, I'll hand back to Morten, and hopefully there'll be some questions. And if you've got any questions afterwards as well, I'll provide my details, and feel free to contact me directly. But just look on the ALS website, and you'll find my contact details.
Thanks, Geraint. So I'm going to open up the forum for questions now. If you could please write your questions out using the Q&A function in the toolbar at the bottom of the webinar. Attendees can also see all submitted questions using this window. While we're waiting, I want to drop a link to a brief survey in the chat. Your responses to this brief 2-minute survey will help us choose future webinar topics. So I will drop that in the chat now. And I also just want to review some brief notes. This webinar presentation has been recorded. All participants of this webinar will receive a follow-up email once the recording is available to view. We will also post our webinars on the ALS YouTube channel in the webinar playlist. I encourage you to find a wide range of video resources and past webinar presentations available there. Also, please follow our company on LinkedIn as we post announcements and registration links to future webinars and other valuable resources and updates. I'm going to hand it over to Morten, who can facilitate the questions.
Yeah, Geraint, the first question, you talked about total organic fluorine method 1621 by EPA and top assay. I mean, how do they compare when it comes to the total concentration in the sample, say?
Sure. That's a good question, Martin. And I know there's our labs in Australia have done quite a lot of work on this. They've got capabilities to do combustion ion chromatography. We see some variation. We do see some quite significant differences sometimes. So we know that the kind of conventional top assay approach does not take into account some of the kind of precursors that are present. So I think, as I said, there's advantages to using two techniques together, and I can see some usefulness in doing that. So that is an approach that is being used more widely as well. So I can see, they're not mutually exclusive. They can be used together, and it gives you an indication of the kind of that kind of mass balance that you would see. So it's a good thing to do. I would recommend people doing that if they've got enough budget to do that. I think that would be a helpful approach to take. But I would say it varies. Some samples you'd see good close relationships, and then other samples there's some variability. So yeah, it's interesting looking at some of that data.
And another question is really, you talked about concrete and how that can be a secondary source. Sampling of concrete, I mean, do you have any input on, how to take samples, what to be aware of, and just general considerations?
Oh, okay, no problem at all. The kind of general good practice about minimizing cross-contamination when we're taking soil samples and we're taking groundwater, surface water samples, the same general principles would apply to concrete as well. So you're trying to minimize any cross-contamination. But typically the way we've been receiving concrete samples is concrete cores, normally about 100 millimeters in diameter. We're able to subsample the very near surface, so kind of millimeter accuracy with the kind of samples that we're taking, the subsamples that we're collecting. But as I said, we found that in many cases that PFAS doesn't impact or doesn't penetrate to significant depth. It's often present in this very near surface. So we've been able to subsample the very near surface and then take sequential samples further down the kind of core. And that allows us to try and better understand how PFAS is penetrating the kind of depth of concrete. And there's another reason for taking concrete core samples as well, which is if you wanted to remove the entire the entire concrete from the site, and then we can take composite samples when we're doing that as well to get an indication of the average concentration of PFAS in concrete as well. So normally two different reasons for carrying that concrete analysis out.
Excellent, thank you. And then I have a question from Tracy saying, would it be possible to get references from you specifically on the interference of precipitation of iron oxide with short chain PFAS?
Yeah, that's absolutely fine. I can send through some more detailed references. I think that has been studied on an academic level. To give you an idea of what concentrations where you'd see that precipitation of iron, and where you might see some interferences with the top assay technique, probably around about 50 milligrams a litre concentrations of iron, you see that kind of precipitation. So I wouldn't say it's a very common problem, but it can be a problem on certain types of sites.
Yeah, so we will make sure that Tracy, you receive a link from us somehow through the email later today or tomorrow. The last one is a fairly technical question I got here, Geraint. It's on iron concentrations in top assay.
Okay.
What can we say about that?
Well, I would probably just what I've mentioned really. I would say just be aware that kind of concentrations of 50 milligrams a litre, we might see that kind of precipitation occurring. As I said, it's not a very common problem, but it's just one of those things maybe to watch out for. Just be aware of. It happened on one or two projects that I'm aware of. But I wouldn't say it's a hugely common problem. You know, there's other kind of limitations that we need to be aware of. You know, I mentioned some about particular acidic matrices as well, where we have trouble raising the pH to 13. That can be an issue. That can be an issue when we're looking at the swabs. You know, it's just I think, you know, with analytical techniques, especially with PFAS, we've got experienced staff that are working on a lot of these projects, and they've got this experience. They know that some of the limitations. So it's having that conversation. I would, you know, maybe emphasize the point about communication with the lab. If you're aware that you've got some tricky samples, please have a discussion with ALS and make them aware that, you know, if you've got really detailed knowledge about these sites. But I would say, you know, that we have got some very experienced, especially in the US, we've got some very experienced analysts carrying out top assay and PFAS generally. But please have that communication with the lab as well.
All right. That was all the questions we had today. So thank you very, very much indeed, Geraint, for doing this, for holding this presentation. We all appreciate it. Alex said, you know, we will send out some additional information, and we are all available for answering questions. And if you need to get in touch with Geraint, you know, you can visit alsglobal.com, or you will find the link, contact information in the email that's being sent out to all of you that participated today. So thank you very much. I wish you a good afternoon, and I hope to talk to you soon again. Thanks, Geraint.
Thank you very much. Thank you, everyone.
Thank you. Bye-bye now.